So here we're looking at probability. And the first thing we want to do is define the law of large numbers. And go ahead and pause the video so you can write that down. I'm going to continue explaining, or at least reading what this says first. The law of large numbers. As the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. Now, to show you kind of exactly what this means, I'm going to do an example here. And it's going to be an example that I made up, but I encourage you to try it at home too. You'll see that it'll work out the same way, or something similar anyways. So example 1, suppose you're tossing a fair coin. Alright, and I'm going to have 3 scenarios here. So over here on the far left, let's say I've just recorded the first 20 flips. So out of the first 20 flips, I get 5 heads and 15 tails. So if I'm only looking at the heads, then that tells me that the probability of a heads is equal to on top is how many of the observations that we want, which is 5, divided by the total number of observations, or flips in this case, which is 20. And what I'm going to do is I'm going to write this as a decimal for now, and that gets you 25%. So just based off of this small sample of 20 flips, we can see that the probability of a heads is 25%. Which we know all is false. We know that flipping a coin, a fair coin, getting a heads will occur 50% of the time. So what is going on here, and why is it different from 50%? Well, let's see what happens as we increase the number of flips. And this is where the law of large number comes into play. It's talking about increasing your sample sizes and increasing your observations. So now let's do 100 flips. And this time, let's say we get 40 heads, I'm just going to label as H, and then 60 tails, I'm going to label as T. So again, just looking at heads only, the probability of a heads is how many observations we want, or that we're looking for, so 40, over the total number, which is 100. And I'm going to write as a decimal just so you can see. We just went from 25% probability of getting a heads now to 40, which is still not our 50%, but it's closer. So what this is showing you is we started at 20 and we increased to 100, and as we increase our sample size, total number of observations, etc., our actual probability gets closer and closer to the real probability. Just one more, let's say 1,000 flips. This time, let's say I kept flipping and now I have 550 heads, 450 tails. So it's the probability of a heads is equal to how many we want, or that we're looking for, divided by the total number. And here we get 0.55, or 55%. So this time we went over the 50% mark with 55%. So it's still not to our 50%, and in fact we went past it this time. So this is what the law of large numbers is saying, though. It's saying as we increase our sample size, as we get more and more observations, the closer and closer we actually get to the real mean, or the real average of whatever experiment we're doing. And that even applies to sample sizes for other observations, not just flipping coins, but this applies to rolling die, and it applies to anything in life, really. That as long as we have a large enough sample, we can say with some confidence that this is what the actual population would be. So just some things to note here. I'm going to say, I'm going to put stars next to these, and this is just so you have in your notes kind of what we talked about here. As we increase the number of trials, the closer and closer we get to 50%. And this is for example 1. And if you were to do this example at home, just do it 100 times and then do it 100 times a different time, and you'll get different answers. But as you increase how many times you're flipping that coin, your probability is going to get closer and closer to 50%. The next thing I'd like to write, it's kind of along the same lines. Now it's just extending it towards a sample. So it's a little long, but we're going to write it so that we have good notes here. As the sample size increases, as the sample sizes, let's say sample size increases, we get closer to the mean of the population. And here let's put in parentheses, meaning if your population is 1 million, and it could be observations, tossing coins, etc. It could be anything. Here we're talking, no, not tossing coins, because we're talking specifically about a sample that we took from a general population of 1 million. This, meaning if your population is 1 million and you take a sample of 50 and a sample of 5,000, the 5,000 is a better representative of the population. Alright, so that's the law of large numbers. As we increase our number of observations, as we increase our sample size, we get better and better, more accurate results in terms of what the population is doing. That's it for now.